All right, last little bit on 5.1, so we have to discuss enthalpy and calorimetry. So here, and maybe you should pause and digest this image up here. This is what a calorimeter will look like. Some variation of that we'll use in the lab. There's also bomb calorimeters, which are more elaborate setups than this, but essentially you're burning something to figure out the energy content involved. Or maybe your reaction is taking place in a closed system and it's affecting the temperature of the water. So an indirect measurement is the temperature we're using the thermometer here. We'll actually do a full-on practical with this, so you'll see how a calorimeter works and you'll get the gist of it. But if you have any questions, see me immediately when you come to class next day and we'll work it out. So the enthalpy change can be calculated using a calorimeter. And so the heat released by the reaction is absorbed by water and it's measured by the thermometer indirectly. And so for the reaction itself, we're going back to use that delta H is equal to NH. So delta H is equal to NH. And remember, this is the enthalpy of a reaction. And so for water in the calorimeter, the water's not going to go through a phase change, and we need to know what the energy input is, or the output if it's endothermic. So here we'll also know that the enthalpy change, sometimes referred to as heat, so enthalpy change can be equal to Q in this sense, and so we know that the delta H here is equal to mc delta T. Now, if you'll notice, the enthalpy change here and the enthalpy change here are the same, so we can definitely set those equal to each other, where NH is equal to mc delta T. This is the more simple way to set this up, and you will have to know that exo reactions give you a negative answer, and endo reactions will give you a positive answer. Conceptually, there's two ways to set these up. Now, so this would be part one, and part one would just have to know your answers are going to be negative or positive. So if you're doing a calorimetry question and you don't want to go further into the analysis, and you just know that it increased temperature of the water, so it's exothermic, or if it decreased, it's endothermic, you can put your sign right on the inside of your equation. Now, to think a little more intensely about this, we know that in a system, if the enthalpy of the reaction, so the enthalpy of reaction, must be exactly the same, so enthalpy of Q, let's say, so the enthalpy of the reaction must be the same, enthalpy of reaction must be equal and opposite of whatever this heat value is, right? So if we're changing the enthalpy, we're changing the heat, those two, because matter cannot be created, or sorry, energy cannot be created or destroyed, it's going to equal zero. And so in order for us to rearrange this, sometimes when we're doing calorimetry, it's important to move the Q to the other side, where we see NH is equal to negative Q. Now, this way down here will always give you the appropriate sign when we're multiplying. So if you have a decrease in temperature, you'll notice that it's negative, so you're going to have a negative and a negative will give you a positive. That means that you'll have a positive endothermic reaction, or vice versa. If you have a temperature increase and a negative value in front, will give you a negative. So this is the more correct way, and you'll be challenged with this in university as well. So when we set up calorimetry experiments, if you'd like to go through the first route and just memorize the two reaction types, you can do that as well. Okay, so there's a couple of things that we can do with these, and I'm going to show you an example using some calculations that we've got from a lab. So let's say that the mass of water in a calorimeter that we have is 200 grams. We know that the temperature increase is 13-degree increase. And the mass of ethanol burned, so this is the enthalpy of reaction that we're looking at, is going to be 0.45 grams. So first thing that we probably should consider is we should probably get ethanol into moles. And so I know that the mass of ethanol, the molar mass of C2H5OH And so the molar mass is equal to, so let's just do this all together, N, the number of moles, is equal to the mass divided by the molar mass, which is 46.08. 0.45 divided by 46.08 gives me a small number of moles, so 0.0097. Let's call that 0.0098 moles of C2H5OH. Okay. Now, so this is the second part. This is used for the enthalpy of reaction. So this is the number of moles that we're using to create energy in the system. And now we have to figure out what the water is doing. So again, from my last little bit, remember that delta H of the reaction plus Q is going to be equal to 0. So in order for us to work this out any further, we know that NH is equal to negative Q, moving that Q to the other side. And so we can start putting some more things into our formula. So NH is equal to MC delta T. Now, I know a lot of things about this. I know that the mass is 200 grams. So 200.0 grams of H2O times, I know the specific heat capacity of water is 4.18 joules per gram degrees Celsius. And I know the temperature change was an increase, right? So remember that this has a negative in front. So this is an increase of positive 13.0 degrees Celsius. So degrees Celsius will cancel, your grams will cancel, you'll be left in an answer in joules. Now here on the other side, we still have our N and our H. And as we put all of these numbers through, 200 times 4.18 times 13, and that's going to give us an answer, a pretty big answer in joules, so 10,868 joules. Now a question like this may not ask what is the energy input into the water, but what is the enthalpy of reaction? So what is the enthalpy of reaction for this ethanol, right? And so this is where we need to do a little bit more work, where H, again, is the enthalpy of reaction, and we'll have 10,868 joules, but we must divide that now by the number of moles of ethanol, right? So the number of moles of ethanol, 0.0098 moles. And so H now, we're going to actually get a perfect value in joules per mole, right? So that's how our H constants are always calculated. So 10,868 divided by 0.0098. And this is going to be quite a large number, so it's 108,979 joules per mole, and because that's such a big number, I'd recommend putting that into kilojoules, so divide that by 1,000, so H will equal 1,108 kilojoules per mole. And really, because of rounding, that should be 1,109 kilojoules per mole for the combustion of ethanol. Cool. We'll do some practice like this in class next day, so please come ready and bring your calculator.